Okay.
Okay, Cristina will talk about the Fredrickson-Andersen two-spin facilitated model.
Okay, thanks, Pablo. Thanks to the organizers for the wonderful invitation. I will present a joint work with Hartarsky and Fabio Martinelli. And I apologize, Stefano, for those that, few among you that you already heard this talk, repetita juvent, so it's not useless. And I also apologize for those that expect PDEs, because there won't be any PDEs for this case, though we would like very much for the analogous conservative version to derive some more interesting things on the hydrodynamics, but for the moment everything is quite stuck. Okay, so let's present the work. So it will be in the part of the title IPS, Interacting Particle Systems. So the model, so it's an interacting particle system that lives on the integer lattice. We will be on ZD. In all my pictures, I will be on Z2. And the dynamics is a Glauber type dynamics, so a birth and death of particles. There are not jumps. It's not conservative. And how does dynamics is defined? We have a parameter Q in the interval 0, 1. This Q will be the equilibrium density of empty sites. And then each site is endowed with a clock, an exponential clock of mean time 1. When the clock on a given site rings, this site will try to update its occupation variable. I'm sorry, I didn't say the most important thing is that it lives on ZD, Z2, let's say, and on each site, there is either a particle or the site is empty. So 0 or empty dot when the site is empty, and the filled dot when the site is filled. So, and when the clock rings, I'm a site, my clock rings, I want to update my occupation variable. And I get a proposal, let's say I flip a coin, an unfair coin, and I want to be updated to empty at rate Q and to occupied at rate Y minus Q. But I'm saying I want to, and I get a proposal because I cannot always accept this proposal. And in order to accept this proposal to be updated, I have to satisfy a constraint which depends on the state of my surrounding neighbors. In order to be updated, I need to have at least 2 empty nearest neighbors. If I have them, suppose the clock rings on this side, I have 2 empty nearest neighbors, so I can update according to the proposal. If the clock rings on this site, no matter which is the proposal, I cannot update. Okay, that's the dynamics. There are questions on the dynamics. It's the right moment.
So
yeah.
The 2 empty nearest neighbor site independent of the dimension. This is like
independent of the dimension. This is the FA2. The 2 spins facilitated is in these 2. Then there are models with
one, like still dimension 1.
Yeah, that's why dimension 1 I don't consider it. You see, I write D bigger or equal than 2 because dimension 1 is a trivial model because it's, as soon as you have a couple of neighboring particles, they will be stuck forever.
Yeah.
Okay, so that's why with this choice of the facilitation parameter, which decides how many nearest neighbors I have to start with dimension 2. Otherwise, I have to consider another model with just 1 empty. But okay, for the moment, we stay in this case in which J equal to 2. I need at least 2 empty sites. At least I can have more than 2. Okay, which are the properties of this model? The first one is a nice property, is that the dynamics is reversible. It satisfies detailed balance with respect to a very simple measure, which is the product measure, which gives weight Q to empty sites and 1 minus Q to occupied sites, which I will call mu of Q. And this is because the constraint does not depend on the 2 updated sites. So when I flip, then I can, the constraint is, the constraint was verified, unless my neighbors change, the constraint is still verified, okay? Second property, less nice, is that the dynamics is not attractive in the sense of interacting particle system. And this comes from the fact that if I inject more vacancies, more empty sites, potentially I can help filling more sites. So there is not a monotonicity, because injecting more empty sites implies that I have more constraints which are fulfilled. And so this can imply that I fill more sites. So this in turn means that some classical tools used to study Glauber dynamics for interacting particle systems, in particular sensory arguments or some types of classic coupling arguments, fail here. Another feature, for these dynamics, there exist blocked configurations. So there exist configurations that are forever blocked under dynamics. A trivial one is the completely filled configuration, but there are less trivial configurations. So if you have a configuration in which you have isolated empty sites, none of the sites has the constraint satisfied, and so it will stay blocked forever. So this in turn implies that this is an invariant measure, but it's not unique. There are other invariant measures, in particular invariant measure concentrated on blocked configurations, but more than that. And so for sure the relaxation to equilibrium cannot be uniform on the initial condition. And also, more technically, the existence of these blocked configurations implies that we cannot use coercive type inequalities to prove convergence to equilibrium. For those that are more in the subject, log-Sobolev type inequalities here do not work. The log-Sobolev constant diverges with the volume of the system, though the dynamics is Glauber, and though the spectral gap is finite. Okay. So another feature is that the dynamics is cooperative. What do I mean by cooperative? I mean that if I have an isolated empty region, no matter how large and no matter of which shape, here I have depicted, for example, a big, not very big because it's a small picture, empty rectangle, this empty region cannot expand by itself, is blocked if it is surrounded by filled sites. So this means that the type of relaxation mechanism cannot be similar to a sort of renormalized exclusion type process in which the empty sites move around. Or, I mean, this empty region should help themselves in order to relax the system. And this will imply that the relaxation mechanism, so when Q goes to 0, is quite subtle, and there is a sharp slowdown of the dynamics. Okay, and summarizing these properties, one first motivation from the mathematical side to study this model is that the model is simple and it has also a simple invariant reversible measure, but new tools are needed for sure to study this model because some of the classic tools here fail. Then another motivation, I don't want to be super short on this, we can ask questions afterwards, is that, at least from my side, the strong motivation comes from the fact that this model, as well as a whole class of models which are derived by changing the specific constraint, there is nothing special in these two empty neighbors, we can study different types of constraint, have been introduced in the 80s by physicists and very much studied in the last since then, because they are used to model the liquid glass transition, which is a phenomenon which is still not very much understood and has a theory for this liquid glass transition is still a major open problem for condensed matter physics. And these types of models in which we have these constraints try to mimic the fact that when a liquid is supercooled and so it's creating an amorphous solid, the glass, the motion of molecules is hindered by the presence of the other surrounding molecules. Okay, so this is a motivation for those that are motivated by physics. And then, so a key question, both from the mathematical and the physics side, is I said that the dynamics slows down when Q goes to 0 because this Q is the equilibrium density of empty sites, and I need empty sites in order to facilitate motion. And so the first question is, how do time scales diverge when Q goes to 0? Where time scale can be the relaxation time, so the inverse of the spectral gap, some heating times, we will quantify them later on. And an observation, so physicists tried immediately to study these questions for this model and for other types of constraints via numerical simulations. And the point is that the divergences are very difficult to capture because the very nature of the problem is that you have to choose constraints in order that this slowing down is very fast. Because for when the liquids is turned into a glass, time scales change very fast. 14 order of magnitude of a change of time scale by varying the temperature of a few degrees. So you are looking for constraints which slow down the dynamics very fast. And often the results from numeric are very controversial. So mathematical motivation number 2, we should try to put on a firmer ground the results from physicists, the conjectures coming from numerical simulation. And indeed, some of the mathematical results that have been obtained in the last 15 years have corrected some wrong conjectures in the physics literature for the behavior of some models. And then a last motivation, and we'll come immediately to this connection, is that these kinetically constrained models and this FA2F, the two-spin facilitated motion model in particular, are intimately connected with the field which has been also very active in probability and combinatorics in the last years, which is the field of monotone cellular automata, in particular monotone cellular automata of bootstrap percolation type. So let's start from this last part, because it allows us to dig more deeply into how the model behaves. So let's introduce another dynamics, which is very a cousin of our FA2F dynamics. It's, let's say, an easier cousin. Let's see why. Of its dynamic, it will be a deterministic, discrete time, and monotone dynamics. Monotone in the sense that while in our dynamics there is killing and creation of particles, here there will be just killing of particles. Okay, how goes this dynamics? Same configuration space, so empty sites and filled sites on ZD. And then at each deterministic time, what we do is for each particle, each empty site remains empty at the later time, while for each particle I check around in parallel for all the particles whether the particle has the constraint satisfied, so it has at least 2 empty neighbors, and if it is the case, I kill the particle. And I iterate these dynamics until reaching a stable configuration, which can be either a completely empty configuration or a configuration in which there are particles which are mutually blocked. Suppose, for example, a configuration in which everything is empty, with the exception of 2 rows, which are one near the other, which are completely filled. All these particles are mutually blocked because they don't have 2 empty nearest neighbors, and so they will stay there forever for this dynamics. So an observation, which you will, it's quite easy, it's very easy to check, is that if I start from an initial configuration and I evolve until this deterministic dynamics, and I reach a final configuration at infinite time when I'm stable, the clusters of particles that remain in this configuration, which can be empty if everything is emptied, corresponds to the clusters which are blocked for the same initial configuration under the stochastic dynamics. Okay, so there is a very important link among the two. So, and this model, which is called the two-neighbor bootstrap percolation, has been very much studied. So the first question which was addressed was, okay, so what happens, since here it's just deterministic, let's introduce a stochasticity. If I distribute the initial configuration in a random way by putting a Bernoulli measure with density Q for empty site, how does the final configuration look? Will there typically be a cluster of occupied sites which are mutually blocked, or will it be empty? And the answer was given by Arnold von Enter at the end of the 80s, who showed that almost surely, no matter which is the initial density of empty sites, provided it is strictly positive, otherwise we are completely blocked, we are in a completely filled configuration, we will always empty everything, which means that under this constraint, a cluster of blocked particles do not percolate, and this no matter which is the initial density. Okay, this is a specific of this choice of the constraint. Then the next natural question is, okay, so we know that we will empty everything, how fast? If I'm sitting at the origin, how much do I have to wait under this deterministic dynamics in order to be emptied? Okay, so one defines the what I call tau BP, the time of the bootstrap percolation, the first time that the origin is emptied under this deterministic dynamic, and how does it scale when Q goes to 0? And so the first paper on this, answering to this question is of the end of the 80s also, by Eisenman and Leibowitz, that proved that this time scales exponentially fast, exponential with an exponential which is an inverse power of Q, Q to the power -1 over D minus 1, where D is the spatial dimension. Later on, 20 years later, Alexander and Royd could prove that, so they just have the upper and lower bounds, that there is a sharp constant here. It was not even clear that there would have been a sharp constant, and he found he also proved which is the value of this constant, this pi square over 18. And later on, Balov, Bolobas, Dominic-Copan, and Morris extended this result to any other dimension, and the proof, I didn't write the expression because it's just an horrible integral, but they found the sharp value of the constant in any dimension. Okay, so now back to our, so this is for the deterministic dynamics. So what does it happen for our model, for the stochastic dynamics, is just describing the behavior of the blocked cluster. But what does happen for our stochastic dynamics, which is, okay, not the important point is not that our dynamics is continuous time, but the fact that our dynamics is emptying and filling. So it's very different dynamics. And so what we did with Ivailo and Fabio, we studied an analogous measure of time scales, which is the first time at which the origin is emptied under the stochastic dynamics when we start in the initial configuration from this equilibrium measure. And we proved that the scaling is the same, with the same type of exponential, again with a sharp constant, which is d times the sharp constant for the bootstrap percolation. So the time for the stochastic dynamics is the dth power of the one for the bootstrap percolation. And I'll spend the rest of the talk trying to explain the heuristics behind this result. Just I wanted to say that the result is not a corollary of the bootstrap percolation result. Of course, we use it. The behavior of this blocked cluster is crucial for us to understand the dynamics, but the mechanism is very different. Our dynamics is not monotone, so we will have to pay a price for emptying sites. We cannot empty everything and just in a deterministic way. And also, even for this model, this result could settle some contrasting conjectures in physics literature that were derived by numerical simulations. Okay, so what's next? So I wanted to sketch the ideas behind proving this result in a very high-level heuristic way. So the first step will be to make a good guess of which is the optimal relaxation mechanism in the low-density regime. And then the second one will be to, once we guess this mechanism, to develop a toolbox to translate these heuristics into a rigorous upper bound for this heating time. It's an heating time of the event the origin is empty. And then we need also a lower bound. And for the lower bound, we will have to identify a bottleneck that is an unlikely configuration set that the dynamics has to visit typically before empty the origin. And this will give us a lower bound for the heating time. A little bit more, so let's go a little bit more inside. So which is this optimal relaxation mechanism? So the optimal relaxation mechanism is the following one when Q goes to 0, is that relaxation is driven by the motion of some large patches of empty sites, patches in the sense that are not completely empty, there will be some filled sites inside, some large empty regions, atypical, which I call droplets, and that will move around in any direction. So the droplets, they are big, they scale as a polynomial of 1 over Q. They will have they are unlikely, they have a density that scales as the inverse of the time that we will find at the end, so exponential minus constant divided Q to the right power. And I said that these droplets move in any direction. So these droplets move in any direction should ring a bell saying that I'm saying something, I'm hiding something under the carpet, because at the very beginning I told you that empty regions cannot move around, they cannot expand. So how comes I'm now saying that I have droplets, not even completely empty, that can move around? And the point is that they can move around with a very few help from the outside. And this very few help will be there because they are big. And see how. So if I have a square which is empty, okay, alone, it cannot, if everything around is occupied, I can do nothing. I can just fill sites inside, but I cannot expand. But it is enough to have an empty site nearby in order to be able to empty, starting from this site, completely this column, and then to refill this column behind, just leaving an empty site. So if I have one adjacent empty site, I'm allowed to expand, to move. And so the point is that I have these droplets which are big enough in order that typically, in a typical environment, when Q goes to 0, around I will have these few additional empty sites, just one per site, which allow me to move. Okay? So they are mobile in any direction in a typical environment. And then, okay, so then what we have to do is to identify these optimal droplets. We want them to be mobile, so to be sufficiently empty, but not too rare. In particular, the thing that I just showed before, so this completely empty region, won't work. Because in order to have an empty site nearby, I will have to have this size of at least 1 over q, actually even more, 1 over q log 1 over q, in order for that to be typical to find an empty site. But if I require a region which is empty of this length, its density will be much smaller. I will have a log correction here, so it won't work. So the point is that our typical optimal droplets will be more, will have a structure which is less rigid than requiring empty columns. So these empty columns of size polynomial of Q are too rigid in order to, they are mobile, but then they are too rare. And so, okay, I won't show this, but we do a sort of multi-scale construction of droplets which have a core which is smaller than 1 over Q, which is empty, and then around they have enough empty sites in order to be able to move this core around, to deform themselves, and then move. So droplets will be some sort of region that can deform themselves and be able to move nearby in timescale order 1, to create a new droplet around in timescale order 1 over the density of droplets, and to coalesce. If I have two droplets nearby, they can coalesce in timescale order 1. So we call this an amoeba-type motion in the sense that they deform themselves, and it is a coalescing and branching simple extrusion process. And we study the typical times for this coalescing and branching extrusion type process, and we find that the times to hit the origin will scale as the inverse density of the droplets, hence the scaling. And then why is this the bit power of the time scale for the bootstrap? Because for the bootstrap, the time scale, if I'm sitting at the origin, I just have to look at the nearest droplet and wait that this droplet ballistically comes to me sequentially. So the time scale for the bootstrap is just the distance to the nearest droplet, which is 1 over the density to the power 1 over d. So, which is the 1 over d exponent of the time. Okay, so so these are the key ideas, and perhaps that's just a few words on the math behind. Of course, we have to do a sort of renormalization arguments of the size of these droplets. We have to study this generalized coalescing and branching simple extrusion type process in order to find the scaling, and we'll have to use the relation between heating times and Dirichlet eigenvalues, use some Poincare inequalities. These are just some throwing some words on the key tools. But I want to come to a last slide in which I'm saying some open problems. So, okay, so just here was just some advertisement to say that the point we were quite happy because the Sharp constant is also for the physicists, because the Sharp constant is hard to grasp numerically. Even for the bootstrap, the correction to the p square over 18 of Oroyd, when he gave this constant, it was a surprise also for physicists, because the correction are such that the convergence is low. But that's why even for the physicists the result is meaningful. And also we were happy because these techniques give us a tool to understand this cooperative relaxation, and the mathematical tools that we use are quite flexible, and we could use them also to apply to the general KCM in dimension 2. Okay, the results that I gave are in dimension D, but for some technical reason we applied them for general constraints in dimension 2, and we got all the universality classes depending on the constraint, which is the scaling of the time scale, which can be exponential, power law, and different type of scaling. But I want to close with the fact that I don't want you to go home thinking that we have solved everything here. Not at all. Everything that I told you is at equilibrium. And we are very much interested, and physicists are very much interested in understanding the out of equilibrium of these models. So two conjectures that I wrote here and that are still open. One is a very easy one that for physicists is just given for granted, but we cannot prove it. Take the same dynamics and don't start from the equilibrium measure, but start from a product measure with a different parameter Q here, which is not equilibrium 1. And then let time evolve. The dynamics should, the time evoluted measure should converge to mu Q, but we cannot prove it because we don't have we can do it for some specific choice of the constraints, but we lack robust tool to tackle this problem. Conjecture number 2, even I think from the mathematical point of view, is even more fascinating. For this model, and in general for KCM, it is expected that in out of equilibrium, a no random limit shape appears. What do I mean by that? Emerges. So we consider the model and take it on Z, say it on Z2 plus, just on the first quadrant, and put empty boundary condition around. And then start from a completely filled configuration, so that inside you cannot do anything, and you have to start from the boundary in order to evolve. Okay? And then follow the evolution at the subsequent times of the size that have already been updated, and rescale this by time. Numerical simulations show that when we do this rescaling, we converge for large time to a no-random limit shape that depends on the constraints, but there is no proof of this result, just in one dimension for a specific model. And this conjecture was started in a paper by Lalle and Kordaskia, which they were studying a northeast model. It's another constraint, and they saw this by simulations, and then problem is still open. That's all.
Sorry.
Yes.
Thank you very much, Cristina.
25 minutes.
Just here, what's the relation between Q and Q prime?
It's just Q is a parameter which is in the coin that you flip when the clock rings, and then it's Q is the probability to set the side to empty. Okay, and while Q prime is a different parameter in the interval 0, 1, different from Q, sorry, and you expect that you lose this memory of the initial different density.
Okay, but we don't know, like, let's say, we don't know Q as a function of the Q prime.
No. This should be true for any choice of Q prime, and you can do this in one dimension. If they are near for any choice of the constraint, you can do this. For some specific models, you can do it in some regimes, but it's not should be true always, unless you take let's say a pathological choice of Q prime in which you stay in a regime in which you have blocked clusters. But for FA to F, you just have to choose it positive, and then you know that there are no blocked clusters in the original configuration, so they will be eaten away, and you should converge to the product. Yeah. Yes?
If I understood correctly, to get this sharp bound, you use you identify an optimal dynamics, which gives you like an upper bound, and
yes.
You also want to have a lower bound. And
yes.
For this, you use the bottleneck.
Yes.
I don't know if you mentioned it somewhere. Can you explain how the bottleneck configuration looks like? Or?
I didn't explain it. That's more. That's quite more technical, but in a sense, the point is that you need to have near the origin, to bring near the origin one droplet. Otherwise, it's too unlikely to unblock it, because typically around the origin there will be a completely filled region of size 1/Q, and then you have to unblock it with a sort of droplet. Yeah.
Non-random limit, the conjecture number 2, non-random limit shape. Does it look smooth in some microscope?
Yeah, so for the northeast, the picture was super smooth. So it seems like for the northeast is the case in which the constraint is north. You have to have the empty site above, and to your right, it was just like a sort of yes, like sort of very similar to things for the ASEP, I think. For the, it looks smooth, but we cannot even say that you fix a direction and we know that in that direction we have a ballistic.
But they're sure it has nothing to do with Borges equation.
I think that once that there should be some some connections to some questions for the, but okay, perhaps we should quit our procedures which are much more microscopical, and we are trying just to prove that given a direction we can prove that the distance of the size which is farther from me renormalized by time, it satisfies a low large number, etc. Perhaps going to the macroscopic is better. I don't know. We discuss this. Yes.
like, I mean, for the second conjecture, what happens if you say just look at the bootstrap percolation for the second conjecture on say Z2? It seemed like we get a corner growth model and get back Berger's equation. No?
Ah, you mean You mean in time? Yeah.
If you're just killing sites, we get like corner growth.
Yeah. Anyway, for the bootstrap, okay, I don't want to. I would say that proving that there is a shape, since you are monotone, it should be possible for all constraints. Then, yeah.
And it seems to me like your previous kind of results seem to say that like the bootstrap percolation is kind of directing dynamics, right?
Yeah, but in one direction. Yeah. Then, yeah.
Okay. No,
We're running late.
No, just a quick question. In the finite volume setting, the time scales have been studied?
Yeah, so in the finite volume, say, for example, the spectral gap is uniform on the, is uniformly bounded from below in the system size, the spectral gap, and diverges as the same divergence as this heating time. The inverse of the spectral gap has the same divergence in density as this heating time. But for example, the mixing time is diverges with the volume. And the logarithmic Sobolev constant diverges with the volume. It's quite universal for this presence of constraints. So they're not so, you should pay something more finer, which takes, but I should go.
Urgent questions? No, the same.